Hi everyone. So we have our full list of shortcuts for this section. I want to sneak in a few examples. These aren't on your packet, they're not numbered, but I want to give you a couple so that you can try the ones that are in your packet yourself and then check back in on the video if needed. So sneaking in some stuff here. Let's start with what is the derivative with respect to x? So this d over dx is derivative with respect to x of 3x squared minus 2x plus 1. I've been saying that one of our goals is to be able to take the derivative of polynomials. So let's do it. And a quadratic is a fairly simple polynomial. So one of the things that you're going to have to start doing, it'll get messier as we go, it's not too bad here, is figure out which shortcut applies first. The way you decide that is you look for the big operation. And when I say big operation, what I mean is the last thing you would do according to order of operations. So if we're thinking about our order of operations, PEMDAS, the parentheses don't count here because it's just saying to take the derivative of that. So we're looking in here. We don't have any parentheses, so we would apply the exponent. We would do some multiplication. There is no division. The last thing we do is the addition, subtraction. So the first thing that we apply are the sum and difference rules. I don't know, I guess it's kind of one rule, one or two, however you're thinking about it. The nice thing is that the sum and difference rule is kind of a non-rule. All it says is just look at these one piece at a time. So first we'll look at the 3x squared, then we'll look at the 2x, then we'll look at the 1. Okay, so looking at 3x squared, the last thing happening there, let's see, we have exponent and then multiplication, is the multiplication. So the next rule we apply is the constant multiple rule, which says if you take the derivative of a constant multiplied by some function, you get that exact same constant multiplied by the derivative of your function. So now we're down to just looking at an x squared and saying, okay, x squared, that's a power function. Variable is in the base. So we're going to drop the power down in front, 2, and then we're going to raise 1, or x to the 1. 2 minus 1 is 1. Okay, so there's the derivative of just the first part. And then the difference rule says there'll still be a minus. The derivative of 2 times x, in fact, what you could do if you want is think about this as hooked together and say this is all one big linear function and its slope is 2, so the derivative of that whole thing will be 2. It's not your only option. You could also do it one piece at a time and say, okay, derivative of 2 times x. Again, you could think about it as linear, or you could think about that as a first power and say you'll have 2 multiplied by 1 x to the 0. And x to the 0 is just 1, so it goes away. And then if you do it that way, you'll have this last piece where you say, okay, I have this plus 1. 1 is a constant, lonely constant, so constant function, and the derivative of that will be 0. So my derivative here is 6x minus 2. Okay, so there's the derivative of a quadratic. Let's see, where's my list of items? Okay, so let's say p is equal to 2c plus 1 squared, and I want to find, and this is a good time to think about this, so if I want to find the derivative of this thing, this is p as a function of c, so it would be the derivative of function p with respect to variable c. Okay, so dp dc. This is actually a little bit tricky because if I ask myself what's the big operation, I have to do the stuff inside parentheses first. So I'd multiply, I'd add, and then I'd square. So the big operation is squaring, which makes me think power rule, but I have a problem because my power rule says that I could have c squared, but it doesn't say I could have 2c plus 1 squared. So for now, we absolutely can't deal with this. If you have a function to a power or a function in the exponent, that's trouble, that's composition. So our only choice is to try and rewrite this. So actually, before I even get started on dpdc, I'm going to go ahead and FOIL this out. So if I multiply 2c plus 1 by itself, I get a 4c squared plus 4c plus 1, and that I know how to take the derivative of. So I've basically rewritten it. Before it was function raised to a power, which doesn't quite fit any of our rules. Now the big operation is the addition, so I can approach it in the exact same way as the last one. I can say, okay, so sum rule first. I look at the 4c squared. The 4 is just going to come along for the ride, And then the derivative of c squared is 2c, so this is becoming an 8c by the time I'm done. And then we move on to the next one. The derivative of 4c is just a 4. So 4 comes along for the ride. C to the 1 becomes 1 times c to the 0. And then the derivative of 1 is 0, so that's all gone. So it ended up being another quadratic, but a little extra step in there. Okay, a couple more. Some of these just look trickier than they really are, and this is one. M of y is equal to e to the pi plus y to the pi plus pi to the y. And I want to find m prime of y. Okay, so I kind of love it because it's rhymey and it looks really tricky. But this just boils down to spotting what each piece is. So the big operation here is addition, which means we'll look at each piece separately. So I apply my sum and difference rule, and it says you can ignore everything else temporarily and just look at e to the pi. E to the pi, so we would want to ask ourselves, I see an exponent, is it a power function or an exponential function? And that would depend on where your variable shows up. But our variable doesn't show up at all, so this is actually a tricky one. This is a constant. And the derivative of a lonely constant, not a constant hooked to something else, but just a constant all by itself, is 0. And now I get to move on to piece number 2. That's a y to the pi. So my variable does show up, and it's in the base, which means this is a power function. So I'm going to multiply by pi times y to the pi minus 1. So drop the power down in front, reduce it by 1. And then last one is pi to the y. So here my variable is in the exponent, which means an exponential function. So I'll get the exact same thing, pi to the y, and then I have to multiply by the natural log of the base, and the base is pi. So just to rewrite it without the 0, I have pi times y to the pi minus 1 plus pi to the y times ln pi. Okay, last one. The last one is find the derivative with respect to n of n to the 4th minus 3n cubed plus 5 over n squared. Oh, I lied. I have one more after this. Okay, so this one is tricky because the big operation here is a quotient, and we actually ran into that when we were learning the power rule, and we run into it again here. So this is one where, once again, before we even start derivatives, we need to figure out how to rewrite the function so that the big operation isn't division. We don't have a quotient rule yet. We can't do that. So here, the way to do it, and there's two ways to look at this, is to just divide the n squared into each of these terms. If it looks better to you, you can make this n to the negative 2 and distribute it in. That has the exact same result. So however you like to picture that. So we're not taking the derivative yet. I'm going to leave it there. I'm going to get an n to the 4th over n squared, which is n squared. I'm going to get negative 3n cubed over n squared, which is negative 3n. Two of those n's cancel out, but there's one left on the top. And then I'm going to get a 5 over n squared, which I will rewrite a little bit. It is what it is, but I'll make it 5n to the negative 2 so that I can take a derivative of it nicely. Okay, so now I'm actually going to start applying derivative rules. The big operation is now addition, subtraction, so we'll just walk through one piece at a time. The derivative of an n squared is a power rule, 2n to the 1, and then the minus carries through. The derivative of 3 times n is 3 times nothing, 3 times 1, I guess I should say. So n to the 1 becomes 1n to the 0, so 3 times 1. And then the derivative of 5n to the negative 2, the 5 just carries down. But then when the negative 2 drops down in front, it gets multiplied. So we end up with a negative 10n to the negative 3. So just to make this look a little bit nicer, I'm going to say that's 2n minus 3, minus 10 over n cubed. Okay, one last one, and I'm just going to sneak it in right here since I'm running out of paper. This is the other thing. I'm trying to get all the little things that mess people up on here. So the fourth root of z cubed minus 2 over the cube root of z. So this is really about exponents, understanding how radicals, roots, and exponents are related. People have trouble just getting this rewritten correctly. Our goal is find f prime, but we don't have rules for roots. And the reason we don't have rules for roots is because roots can always be written as exponents, and then we just use our power rule. So I'm not taking any derivatives here. I'm just rewriting the function. The fourth root of z is the same as z to the 1, yeah, I guess that's true. How about we say it this way, though, because it's a z cubed. A fourth root is exactly the same thing as raising something to the 1/4 power. So we really have z cubed to the 1/4. And then as a cube root is the same as a 1/3 power. Because this is in the bottom of the fraction, I'm going to rewrite even a little bit more and say, okay, well, that's the same as 2 multiplied by z to the negative 1/3. So the negative would put it in the bottom, and the 1/3 makes it a cube root. And then I'm even going to do one more step. Here we can multiply those exponents. So we have z to the 3/4 minus 2z to the negative 1/3. And now finally I'm ready for the derivative, which is going to be power rule. Drop the 3/4 down in front. Oh, big thing is the difference, but that means look at one at a time. And then the new power is 1 less than the old power. And then the minus, okay, so the 2 carries along, but then a negative 1/3 drops down in front. So this becomes positive 2/3. And then we have z to the negative 4/3, 1 less than the old power. And then I'm just going to rewrite. So I have a 3 over 4z to the 1/4 plus 2 over 3z to the 4/3. And you can put that back into radical form if you'd like to. I don't care. I have no preference on that. All right, thanks for watching.